Cool. So I'll just go ahead and get started. I'm happy to keep this very interactive since a lot of these slides are actually a rehash of the Lisbon talk, but I have a little bit of new content. But today I'll be talking about scaling trustless DNN inference with zkml and also some potential applications. And to get this, to get everyone on the same page, well, ML is eating the world. So things like ChatGPT, Bing Chat, Bard AI have been seen a huge amount of increase in interest, but also things like recommender systems, for example, in the Twitter algorithm, all the way down to things like Midjourney and Stable Diffusion to generate images. And so one question that we'll focus on in this talk is, can we execute ML models and also just pipelines more generally in a trustless manner? In other words, we don't want to necessarily trust the provider of the ML model to employ in these various applications. And I'll describe why we care about this later in the talk. So one just broad thing in cryptography, which I'm sure this audience is very familiar with, is the notion of verifying computation. And there's a few ways to go about doing this, including multi-party computation, homomorphic encryption, and zero-knowledge proofs, which is what we'll be focusing on today, obviously. And so zero-knowledge proofs can prove the computation happened correctly, and anyone can verify. In terms of the performance considerations, they can give privacy and and I'll describe actually specifically what we mean by this in the coming slides, and validity, and there's no interaction required. And this is very important because in some applications, we want people to be able to unilaterally post proofs without having to necessarily have all the parties be online. Unfortunately, there's a high compute overheads, and so in this talk, I'll describe how to construct efficient zero-knowledge proofs, specifically efficient circuits for ML and the various applications, and also for image edits, and also why we care about this. Now, one thing I want to be a little bit specific about in terms of the notation is what specifically these zero-knowledge proofs are doing. So here we're going to use this notation f of x comma w, where f is the function that is shared between the prover and verifier, w is the private input, x is the public input, and pi is the proof. The verifier will take pi and then can verify that f ran correctly without actually knowing what w was. And importantly, these proofs can be computed on demand after the fact. One thing I want to point out here is that what exactly x and w are actually changes quite dramatically from application to application. And then there's this unfortunate notational confusion, which is here, this w can sometimes mean weights in ML land, but I'll be very specific and say that here w just specifically means a private input. And I'll walk through several examples of how these can change depending on the application. And speaking of applications, I'll walk through three of them and that are open source frameworks zkml can enable, starting with trustless audits. So why do we care about trustless audits? You might want to have a variety of applications, for example, proving that you run an FDA-regulated model, or for example, proving that your Twitter timeline isn't biased, given the recent interest in social media recommendation algorithms. But beyond this, there's this general concept of you have an ML service provider, and this could be Twitter, this could be an ML model provider, this could be OpenAI, and you have a model consumer. And so here I'm showing a specific example of classify the image, which falls under the first use case of the FDA-regulated model. But you could also actually imagine this being Twitter, where the model consumer is actually the user, but they don't actually have access to the data. And here the model provider might either serve a correct or incorrect prediction. But again, for example, for the case of Twitter, you might imagine them censoring some tweets. And so there's this big challenge of, can we verify that an ML model was actually run correctly, which today we just have no way of doing. Now, one core primitive that we'll use throughout this talk is computing this function f of xw for inference, or the forward pass of a machine learning model. And I want to describe what I'll call the functional view of inference, which is actually not necessarily how this is described in most of the ML literature. And here I'm denoting this function forward to be the inference function, essentially. And in the functional view, we take as input the weights and the data, and then produce the output. So here for inference, typically what you want to do is you want to have commitments to the weights, data, and output. And typically the weights and data are hidden, and typically the output is actually revealed. But you can actually even hide the output depending on your application. For example, if you want to reveal it at some later point. But so even though this starts with W, it's these weights here are actually hidden when translated to the zero knowledge proof. Now, beyond inference, we also might want to, in fact, produce proofs of training for full end-to-end trustless audits. And the way this will work is that we first commit to the training data, for example, these going back to the FDA use case. And then we produce zk snarks of the training process, which is typically done using a process called stochastic gradient descent. And I want to be also very specific about what F is for training. And here we'll take a functional view of inference and SGD. So as I mentioned before, for inference, you take in as inputs weights and data and return the output. But in SGD, you actually take in the weights and data. And here it's actually typically you'll also have a label as well, but not necessarily. And then you output new weights. Now this is very important because like what actually typically for SGD, you actually want to change what is public and what's hidden. And so typically in X, what's public are commitments to the weights, both the old weights and the new weights, and also a commitment to the data. And so if you go back to the previous procedure here, that's how you can confirm you're using the data that was committed to in the first phase. And what's hidden are the weights, both the old and the new, and the data. So by doing this, you can in fact unroll the full SGD procedure sorry, excuse me, some allergies. You can unroll the full SGD procedure without actually ever revealing the data or the weights.
Could I jump in with one question?
Yeah, go for it.
So here we're talking about like the function is the forward pass function is taking in weights and data. So seems like I'm thinking specifically about like the model architecture. So like the model architecture would be fixed, like the sort of like F that we're evaluating on weights and data would be fixed. And then like OpenAI, if they want to prove that they're conducting inference correctly, would need to reveal potentially an architecture that maybe they wouldn't want to reveal. Is there any way to have the architecture as a private input or something like that, or is that not realistic?
Yeah, so there is some work around committing to a function in a function family, I believe by Dan Bonnet. As far as I'm aware, this work is not practical for machine learning today. But as we push forward these technologies, hopefully they will be in the future. So you're right that OpenAI wouldn't want to use this, but there are other applications. For example, the Twitter algorithm, the FDA models, and also, as I'll show in a bit, the prompt marketplaces, and also biometric authentication that you are okay revealing the architecture.
Got it. Thanks. Yeah, and I remember like when Llama came out, they released the architecture open source, but then kept the weights private. So that's sort of this paradigm here, I guess.
Exactly, yeah. So Llama is actually a good example. Let's say you have some secret sauce fine-tune like RLHF dataset. You could imagine fine-tuning Llama and saying we have the secret sauce which we trained our model with, and then we can actually have people verify that we ran our secret sauce model with the public architecture.
Right. Cool. Thanks.
Cool. Okay, yeah. So now that we have, so once we have this proof of training, and here this W is the committed weights, which the verifier doesn't know, but the prover does. We can then do test time audits. And I apologize for this F here again, but this is what we'll call an audit function. And this is typically done using like the forward pass function. So you can imagine doing audits of the form, say the data isn't biased, the model performs well, other kinds of audits as well, depending on the specific application at hand. For example, that Twitter isn't censoring your tweets or the other things. And this combines both the forward pass and also the SGD as well. So this is one specific example where you keep the weights hidden the entire time. You never reveal the weights in this procedure. Okay, so now I've talked about trustless audits. I also want to talk about decentralized prompt marketplaces, which is a slightly different application and also, in my opinion, a kind of fun application. So in general, generative AI requires prompts. For example, if you want to produce this image using Stable Diffusion, you can use the prompt an astronaut riding a horse. And as these generative AI methods get better, the prompts become more valuable to generate. So for example, on the left-hand side here, the full prompt is something like cinematic off-center to shoot 35mm film of a still 30-year-old French man, curly brown hair with a stained beige polo sweater, reading a book, et cetera, et cetera, et cetera. And as you can see, these prompts are very, very detailed. And so if I try to generate the image on the right, I might say something like, drip pope, which is obviously a terrible prompt to attempt to even generate something like this. And the reason that this is important is that there's now these jobs called prompt engineers, which can pay quite a bit and don't necessarily require a background in tech. But you might imagine that there's some examples where you might want to contract out some prompts where you don't necessarily want to hire people full time. And so ideally, you'd like to have a marketplace to purchase prompts. And the fundamental primitive that you need to have a marketplace like this is to have hidden inputs and public outputs. And you ideally want to have a ZK snark that takes in the hidden prompt and outputs the image from the prompt. And here again, the F actually changes. Going back to the functional view of inference, the forward pass is the same. But what's different here is actually the weights are public because these models that we're using, we're assuming are publicly available. But we instead commit to the data. And so this way, the data, the prompt in this case, can be hidden. And so that way, the person with the prompt can either sell the prompt itself or compute modifications of the prompt and then sell the outputs. So again, what exactly is public and what exactly is private changes depending on the application, which is one of these things that's confusing about zkML. The last application I want to talk about is trustless biometric authentication and also fighting deepfakes, which go hand in hand. So first, what are deepfakes? Well, deepfakes are images or video of a person in which their face or body has been digitally altered so they appear to be someone else. And this is typically used either maliciously or to spread false information. And unfortunately, these deepfakes are on the rise. They've actually been used or attempted to be used in the Ukraine-Russia crisis. They've also been used to trick businesses into miswiring funds and also to fool unsuspecting customers into wiring funds to scams. And as generative AI gets better, these deepfakes also get better as well. So it becomes an increasing problem.
Help.
So one way that we can help prevent deepfakes is to use what are called these attested cameras, but more broadly, we can use attested sensors. So this includes things like microphones, depth sensors, and others as well. And you could even imagine in the future attested keyboards. So these attested sensors have this core primitive, which is that they sign the photos or whatever comes off the sensor immediately upon being captured. So you can verify that this sensor took this photo, but not this one. And these signatures have all the same properties of cryptographic signatures that we love and know. So you could basically think of them as being unforgeable. But in many circumstances, photo editors might want to edit images privately. So for example, we might want to crop out some private credit card information in this example on the left, or say crop this picture here to just contain the face for say Face ID. And so in zkImage, we designed a library to attest to image edits securely and privately. And the way this works is that given a hidden input, we can compute the edited image both privately to keep the original image hidden and also securely to ensure that the edits were done honestly. I want to go back to this to what exactly f is for zkImage. And let's go to what I'll call the functional view of an image edit. So we have some edit function, which takes in an image and outputs the edited image. And so in zkImage, X is the commitment to the image, and W is the edited output image. Okay. And actually, one of the things I want to point out is that, sorry, I messed the slide up. Sometimes you actually want to keep the output image hidden, but only reveal a commitment to the output image. And we'll talk about why we care about this in a few slides. But for the time being, let's assume that the output image is revealed. Now, for the finding defects scenario, what we want to do is we want to place this in the larger context of what needs to be done to actually deploy this, for example, say for social media. Well, because social media consumers are consuming these photos whenever they see it in their timelines, excuse me, the original image taker can't necessarily be online. So what you need to do is you need to register the signatures of the original image and also the proofs into some registry that when the consumer of the photo sees the photo, they can also download the proof and the signature and then see that the edited photo honestly came from the original photo. One thing that you might also need to do is attest to multiple edits. In this particular case, what the inputs and outputs what's private and what's public is actually changes as well. So so in the first proof that we're producing here, the hidden input is the image, and what's output are the commitments to the original image and also the commitment to the intermediate edited image. And similarly, for the second step, the output is the commitment to the intermediate edited image, and the output is the revealed image. I said that sometimes you want to actually commit to the output as well. And the reason that we might want to do this is to actually run Face ID in a trustless manner. And what I mean by this is that we can use zkImage to privately edit a photo, for example, to crop out someone's face, and also execute a Face ID model. And this is done entirely privately. And the only thing that gets output is that whether or not this person's face matches a face that they registered previously. And the only thing that's made public is the proof. So the image is kept entirely hidden, and actually, in fact, the Face ID embedding is also kept hidden. The only thing that's revealed is does this authenticate or not. So going back to this notion of what's public and what's private changes depending on the application, this is another example of where you actually want to keep the output image hidden and only reveal a commitment to it. Okay. So now I want to talk about our open source framework, zkml, which enables all the applications I mentioned previously.
Can I ask a quick question? Like more of a practical question. So like, yeah, I think this sort of like framework for image editing and image cropping to preserve like the authenticity of a image is important. And it could theoretically, like the same exact thing could be applied to audio processing. And I'm just wondering practically if you've seen any projects that are doing the same thing for, well, I guess all of this like relies to a camera that signs its photos. So I guess you would need a microphone or something to sign its audio output or something like that. But I don't know, have you seen any projects in that direction? Because I think that'd be a very useful thing, especially with all these voice models that are coming out now.
So are you talking about the hardware or are you talking about the software on top?
I guess both, because practically you would I guess need both.
Yeah, for the software, keep your eyes peeled for in a couple of weeks. We should have some announcements. In terms of the hardware, it's very difficult to convince hardware vendors to put some features onto a device without showing that there's some demand for it. Kind of the chicken and egg problem because hardware is expensive to manufacture. Um,
I
Now, with
see.
that being said, hopefully people will see that this is going to become an increasing issue, and then some of the work that so you can actually emulate this pipeline by signing the data with a private key, for example, with your like a publicly doxed wallet or something. And so hopefully we can encourage these hardware vendors to think more about validity of data as well, and then we can push towards this direction.
I see. So like instead of the microphone directly signing something, if there's some audio that's online of me, I can directly sign that with like some key that everybody knows is really me, and that effectively is functionally the same, and then you could do whatever processing on top of that. Okay, cool.
Yep.
So it sounds like you guys are working on that. Is that the first like project in this space on this audio this ZK audio editing?
That's a great question. I'm not familiar with any other work in this space, but there's more and more people working in this area, so it's hard for me to say if we're it's hard for me to say exactly.
Cool. Yeah, like I guess the main like commercial uh application that I would think of, I've been seeing all these like fake Kanye West or like Jay-Z's popping up in songs, and it's like impossible to distinguish them from real, and that that will eventually have very serious like legal probably implications, and so I could see there being monetary implications there definitely. um, anyway, cool,
Yeah,
thanks. Looking forward to that work a lot.
yeah. And beyond that, there's also like lots of copycats and scams of Elon Musk, any celebrity that you might have heard of under the sun, fake ads, you name it, it's out there. So hopefully people will start to pay attention to this more.
Yeah, another question I want to ask. I understand that what Andy mentioned, like if someone, like if I recognize my voice, I can sign this audio. But it seems like it's very hard for Elon Musk to sign like his photos, right? I think the motivation is still like it comes from a camera directly instead of being edited. So it seems like you have very high requirement for the hardware vendor. It's not only like the vendor want to add this module, add this kind of signature module to the camera, but it seems like for this like model to make sense in real world, you might need some kind of trust environment stuff to kind of embed your keys into that device, or because hardware vendors might do something bad and you don't know, like maybe it's like one camera have one key which you can't kind of using some way to get that private key, or like you can just sign any arbitrary stuff, right? It seems like this device encryption still has a very hard requirement. It's not only the marketing demand, but also like you might need something like SGX chip inside some camera or whatever. Yeah, I don't know.
Yeah, so I think the way to think about it is that it's the same difficulty as creating like a ledger, like the hardware wallet. If you think ledger is secure, then this should also be very possible to make secure as well. Because what you need in the signing unit is you only need to keep the private key hidden, and then you just need to put it next to the sensor, and then assuming that you can't like sorry. I will say that like for any level of security, for any whenever security meets the real world, there's always hacks around the around specific security models. So for example, even for a ledger, someone can put a gun to your head and say, "Hey, if you don't tell me the seed phrase, I'm going to shoot you," and you're probably going to tell them the seed phrase. Similarly, for an attested camera, even if you have like the assigning unit soldered next to the sensor, someone could you could imagine someone like physically taking it apart to get the signing unit separately. But again, like when security meets the real world, there's no guarantees you can make. So the point here is to raise the cost of attacks, not to necessarily to guarantee unconditional security, which is unfortunately only possible in theory land.
Yeah, that's exactly what I'm asking, because I think it's even much more difficult than putting a ledger into such a thing, because ledger is like, your private key, you just keep that in your ledger and secretly. But I think for this device to be secure and trustless, you need someone like, even like vendor and you don't know the maybe the private key or whatever. It's just embedded in some kind of unhackable like hardware black box, which is like SGX or some other stuff, so that you can't hack. You literally can't hack. You can only use some side channel or whatever to get the information. So only in this way you can make sure that this device is neutral, or you are kind of relying on vendor or like the people who are taking this photo, and which is kind of different from what you want. You want people to know that this photo is come from this camera, and you don't want to trust the vendor. You don't want to trust people who are like taking this photo. You just need to prove that you verify that it's come from this camera directly. So it seems like it's much harder than even putting a ledger into a camera.
Okay, so there's a couple of things to say about this. So one is that it's actually very common to have manufacturing processes where you have a private key embedded to a device and you throw away the key. So for example, this is done in SGX where they manufacture the chips, and it's also done on many Android phones as well, because there's like this root, also iPhones as well, because there's like this like root certificate that they use to sign the enclave. So for example, the iPhone actually has an enclave on it. So the hardware manufacturers are actually very cognizant of this issue, and they in fact know how to do it. It's just there hasn't been demand for tested sensors, so they haven't done it for these sensors. Now, in terms of the security of the ledger versus the signing unit next to the sensor, it's the same thing if someone steals your ledger. If someone steals your ledger, and if you assume that they can take the private key off of it, then that's very bad. Similarly, if you assume that someone can take your have access to camera and then rip off the private key, that's also very bad. And there's ways to hardware ways to help make this process very difficult. The other thing I'll say is that I guess I'm gonna like repeat this, is that whenever security meets the real world, there are no guarantees. You could imagine like having like some very expensive piece of hardware that like some governments have to hack some of these physical devices. Similarly, for a ledger, someone can kidnap you and put a gun to your head and say, "Tell me your seed phrase." So you need to have a multi-pronged approach. Now, specifically for these attested sensors, you also ideally want to have a reputation attached to these public keys. So for example, if one public key is producing tons and tons of data that you're pretty sure is fake, you might want to then blacklist that specific public key. So this needs to be combined with other methods, for example, reputation, to ensure that the process is as secure as possible. But I also want to hammer in again, once you meet the real world, there's no system that guarantees full security, unfortunately.
Yeah, that makes sense. Another like attacking example I can think of, especially for audio, is that maybe you can just play some fixed audio and then like you can use another device, which means your input data is already being fixed, which I don't know like whether you can use some FFT or like whatever frequency to figure out whether it's like you are like recording some faked video or it's real voice. But yeah, okay, that makes sense.
Yeah. That's also a great point. So for images as well, you can take a picture of a picture. Like you can literally just print out a picture and take a picture of that. So there's many potential issues here. So for cameras, the solution in the long term, I think, is to have every camera be a depth camera. So if you have the depth data associated with your image, then you can tell if something is flat or not, and then you can flag that. Now for audio, this can be a bit difficult. But you could also imagine doing something like have like a lot, for example, like a lot of advertisements or podcasts or both video and audio. You can imagine them being signed together, so you can just like kind of check if the audio matches the say the movements on someone's mouth or something, and then use that as sort of a multi-pronged approach to attempt to solve this problem. But you're exactly right. There are many practical issues that need to be ironed out, and what exactly is secure and what exactly is not is still up in the air. But I think that there's going to be a lot of interest in this, and we need to move towards this direction. And without the hardware, we're hosed. There's just like no way of doing this in software.
Okay, cool. Thank you.
Andy, did you have a question?
No, I was just gonna ask about the like depth sensor is a good maybe solution for video, but yeah, audio seems harder.
Yeah, certainly. So many things to be figured out, but I do think that having the hardware in place will serve as a ideally spur some development on the software side as well. Okay. Yeah, so again, feel free to interrupt me if there's any more questions. But if there's no more questions at this point, I'm going to go ahead to the next part of the talk, which is our open source framework, zkml. So if you look at the prior work for ZKPs for DNN inference, and also actually for image edits, all the prior work really works in these unrealistically small images. And for image edits, the largest that I'm aware of goes up to around 300 by 300. Whereas in this work, we describe how to scale these zero-knowledge proofs to ImageNet, which has 1,000 classes and also realistic image sizes. Yes, unfortunately, as I mentioned, I didn't have a chance to really go deep into the details of how we do this. But there are a number of very important choices around ML models, including the architecture, how you arithmetize the architecture, and the proving system. And all these are very important for high performance circuits for zkML. So as some examples of considerations, floating point arithmetic is very, very expensive in zero-knowledge proofs. And there is some work, I think, from Don Song and others to try to emulate floating point exactly in zero-knowledge proofs, but their overheads are unfortunately so high that they're not practical for machine learning. And so we need to quantize these models effectively. And then given these quantized models, we then need to optimize the layout within our framework to then achieve high accuracy. One thing I will point out from a technical detail is that, as it turns out, rounded division is actually very, very, very important for high accuracy. So you need to do rounded division. You can't do standard integer division for deep neural networks. What's also important is how you actually lay out the circuit itself. And so we do linear layers via custom gates, non-linearities via lookups, and we do some intelligent fusion in terms of like when exactly or when and how we use these lookups to do the fixed point arithmetic, this rounded division efficiently. To use zkML, all you need to do is clone our GitHub repository and then run it on our example, and this will prove an MNIST circuit in about, the proving time is about 4 seconds, I believe, on my laptop. I'll talk a little bit about our evaluation. So we, for ImageNet, we used these MobileNet version 2s. We measure some metrics, including accuracy, key generation times, and proving and verification times. So if you've seen our preprint, these are the numbers that we have in our preprint, but in our open source release, we can achieve 10% higher accuracy. I think actually a little bit more than this. It might be like 12 or 13% higher accuracy. 6 times cheaper proving from moving from IPA to KZG. Sorry, 500 times cheaper verification from moving from IPA to KZG, and also 6 times cheaper proving by using some improvements in the circuit layout. And actually, one of the big improvements in proving it comes from the fact that we can use cheaper instances because we use less memory, and this ends up being a big deal in terms of the cost. Right. So in terms of how this translates to actually real world applications, let's say we want to verify a private model's accuracy. Well, in our paper, these are the total costs, and with our open source release, they're substantially cheaper. And if you want to compare this to say $85,000 for a monetized data set, you can see that these costs become suddenly look very reasonable. And so to conclude, we're increasingly interacting with digital systems, and zero-knowledge proofs provide trust in the face of adversaries, and this includes for ML models and also against deepfakes. Our framework is open source for anyone to use, and my email is here, Twitter's here as well. But I believe we have some time to take any questions as well. So happy to have a free-form discussion, answer any questions or anything else that you guys might want to talk about.
Awesome, thanks. On the previous slide, that like sort of cost of verification, that like I'm just imagining like maybe you have some marketplace of models and they advertise their accuracy and then people can check against it. Like if multiple people send challenges, then everyone can verify all the challenges that everyone else has sent, right? Like it's not like I need to spend $400 to evaluate this thing all myself. It's like if there are multiple parties that are interested, they can split this cost and have the same effect basically because they can all verify all the previous proofs, right?
Yeah, that's right. If you trust the other people participating, then you can do this.
But do you need to trust the other people? Like, because the output may be public, right?
You need to trust that the other people participating in this protocol, so not the model provider, the other people providing the test set, aren't colluding with the model provider. So, for example, like if you're let's say in the fully anonymous setting, because I think this is the case where it's the easiest to describe.
Yeah.
The model provider themselves can pretend to be participating in this verification protocol and basically upload some bogus data.
I see. But the data, the like challenge data for classification will be public, right? Can be public.
It could be public. You could also imagine scenarios where the people who are doing the verification or participating in the verification want to keep their test set private to themselves and only to the model provider. But even then, like you could imagine submitting like data that was like in the training set or something, so it achieves high accuracy, so it can artificially increase the accuracy.
I see.
But if you and like, oh sorry, go ahead.
Oh no, go ahead. Yeah.
Yeah, but on the flip side, if you and let's say like you're running a particular kind of service and you want to like get together with like the 3 other companies in the space running the service, you can all like pool and you all trust each other to not mess with the verification process. You can all contribute say like a third of the examples and the costs as well. So there are ways to split this if you trust the other people in the verification process.
Got it. Cool. And then I had like more of a technical question. I don't know whether you can maybe elaborate on the non-linearity part. So like just the one-liner was like using lookup tables for non-linearities. Then like how do you actually prove the lookup table non-linearity is correct? That's still like are you doing that in circuit or like is that are the lookup tables like public inputs? Yeah.
Yeah, so actually this is one of the things I need to figure out exactly. The lookup tables we assume are public. I actually don't know if that like our implementation is that way, but they're fixed at the circuit construction time.
But how does that work though? Because so what is the sort of like interface of the lookups? It's like you have some, I don't know, what's an example of a non-linearity? Like tan H or something, and you have some input, and then in the lookup table you would have the input and then the tan H of that input. But the values in that lookup table will be different for each forward pass of that model, right?
Oh, right. So what you do is that there's a possible range of inputs, and then you just have a table which describes all the possible inputs, and then it maps the outputs. And then all you have to do is show that like this tuple of input output of like this activation in the forward pass is in this table.
So you could enumerate all the possible inputs to all of your nonlinearities.
Yes. You can
how
do this
many
if you do.
how many like general, like what's the dimensionality of that, I guess?
Yeah, so this is why the quantization is so important. For the models that we've done, it's something like it depends on the model. It's somewhere between 2 to the 22 to 2 to the 25, let's say, ish.
I see. And are there on any like functions that you need to deal with that take, for example, like 2 inputs? Because then you'd like double the size that you need for your lookup table. Or do they normally only take in 1 input, and so just like hard coding some, it's just like brute forcing some lookup table of size 2 to the 22 is good enough?
Yeah, so it depends on the lookup. There's actually one non-linearity, which is a vector function non-linearity called the softmax, which is like particularly challenging. And in fact, as to the best of my knowledge, there's been no circuit for the softmax developed until we wrote it. And you need to do a bunch of tricks there to make sure that the softmax is high performance. The other non-linearities I consider are point non-linearities. So they go from one input to one output.
Got it. I see. So I see. One input, one output can be used for, you can use a lookup table, a pre-processed lookup table, and then for something like softmax, you need to actually write an expensive circuit.
Yeah, the softmax is actually very expensive, but it's actually turned out to be critical in a lot of applications people care about, including language models,
Right.
Training, and some others as well.
Got it. Yeah. So like in the ZK APM, we do like, for example, we use lookup tables for things like Ketchak, but with Ketchak, it has like variable length input, and we can't actually enumerate all the possible input output pairs. So we need to basically use dynamic lookup tables where at witness generation time, we dynamically populate the lookup tables, but then we end up needing to prove actually like the validity of those entries in the lookup table anyway. So yeah, but okay, that makes sense. Thanks for answering my question.
Yeah, and actually one of the features that's turned out to be really useful is this just in general, is like the random linear combination feature where you do multiple passes over the over the circuit. So this actually ends up being very useful for certain kinds of operations as well. So there's lots of tricks that you need to do to get these high performance circuits.
Yeah, I think one optimization maybe you can do in the future is, I think there are some new lookup schemes which is extremely efficient for large lookup tables, and I think CQ, and which you can pre-process, and you can maybe use your table size to be 2 power 32 or something, so it can maybe massively reduce the overhead and also expand the lookup range you can use. Another question I want to ask, because I'm not in AI space, so maybe it's totally wrong. So I'm curious about, I roughly remember there are some work which you can use some kind of Taylor expansion or whatever to express this, maybe some functions you use in your like neural network. Is that something like which can be helpful, so that you don't use lookup, you can use some kind of other custom gate for those polynomials to emulate some range? I don't know, maybe is that because like, I don't know like whether that's a valid solution or not.
Yeah, so the ML space is very, very wide. And so here's what I'll say about this. In practice, if you talk to people who do ML like who actually deploy ML like in production, they're very, very sensitive to how the neural network architectures are, and there's like a limited set of things that they're willing to consider, even with something like neural architecture search. And the reason is that there are many kinds of proposals that have come up in the academic literature and also in the practical literature that work really well on one data set or one set of examples. But when you try to use them more broadly, they somehow don't perform as well. So convincing practitioners to switch their nonlinearities can be quite challenging. And so, for example, if you look at something like Llama, where the cost of training is very, very high, and the training processes are very bespoke, they're very, very reluctant to change the nonlinearity because like the training process, the training cost is like $10 million or something. There are some ways you can approximate certain kinds of functions with with these custom gates. For example, like the ReLU is one example of this, which is like max, the function ReLU of x is equal to max of 0, x. And here you can do a bit decomposition and then set the sign bit equal to 0. So that's, or yes, and sign bit equal to 0. And so that's one example of where like there's an alternative approach to doing a nonlinearity besides a lookup table. And here the cost of whether or not you should use a lookup table or the bit expansion depends on the number of times you're doing the non-linearity basically. So there's some considerations here in the circuit design which ends up being very important to practical performance.
Okay, that makes sense. And so by saying like optimize layout in your framework, are you optimize this layout means your neural network architecture layout, or it's some other layout like circuit layout or what?
The circuit layout. It turns out how you pack the circuit is very important.
Okay, I see. That makes sense. And do you anticipate like in the future there might be something for zk machine learning like PyTorch where you can automatically do this kind of circuit? You just have some like maybe core kernel written in some custom gate form, and then you can combine that and then like automatically doing some like optimization. I don't know, like what do you anticipate the future will look like? That people need to write circuits, or they can use some toolings to automatically generate circuits?
Yeah, so our framework does this for you. So you don't have to write the circuit by hand. You only need to provide the math specification and compile it.
So what do we see as the biggest bottleneck for adopting zk machine learning in real world? Is I guess it's proving overhead, but like which part do you think is the most like difficult part to optimize, and how large is the circuit?
Yeah, it's definitely improving overheads. And it's hard to say because unfortunately every part of the machine learning process is expensive. I'm excited by CQLin. I'm excited by CQ because you can have these bigger tables, which are very useful in many circumstances. But like one of the issues is that if you roll your own crypto, then there's this question of like, oh, well, how do you know it's battle tested? How do you know it's ready for like actual like use? So I think there needs to be this process of getting these like advanced methods into open source proving systems so that they can be used and audited by a wide range of people. Yeah, it's hard for me to say because there's a lot of factors that need to be in the right place for this to be widely used. Like as I mentioned, like even if you can make like your own crypto system that's very, very efficient, you still might want to be very sure that like there's no security issues and other things. So it's quite a challenging process.
Okay, that makes sense. So it seems like you want just more efficient proving system to generate for your existing circuit and architecture. You won't consider like maybe some kind of model and like proof system call design where you kind of replace some parts like to be more zk friendly and like have some kind of call design process there. Maybe it's not the case for machine learning because people just in practice don't want to use other replacement for their functions in their network.
It's pretty tough to convince people to switch what they're using in terms of the functionality of their network. Yeah.
Sounds like EVM.
Yeah.
I guess you guys have a lot of experience with that.
Yeah. Anyone have any more questions?
I have a question here. I'm wondering if you have considered other proof systems other than Plunk or Halo 2, maybe Plunky 2 or other proof systems out there.
Yeah, so I was thinking about Plunky 2. I was told that someone told me at some conference that that lookups were coming to Plunky 2, but I haven't seen any news of this. That would be amazing if it did, because then I would love to play around with it. Plunky 2 is also
Actually, hey Daniel, I think I kind of remember actually talking to you about this at ZK Summit 9. And so what I found out is there's like an unmerged branch in the Plonky 2 repo that implements like the lookup argument that some guy presented there.
Oh, really?
I think I haven't tested it out myself, but the code's there.
Oh, okay. Actually, John, could you send me an email with this information?
Yeah,
Because I want to check it out.
for sure.
Yeah, let me just flash my email up on the screen again, so you have that if you don't already.
Can I just throw it to your TG?
Yeah, that works as well. Yeah.
Okay.
Okay, so apparently there's an unmerged branch with lookups, so I guess I'm going to check out Plunky 2. Yeah, Plunky 2 also has some annoyances in that it's they're very, very opinionated with how you do circuit design, which is unfortunate for a wide number of reasons. Like because for like zkml specifically, like you really want to have control over how the circuit gets laid out. But you know, there's also exciting developments, at least folding schemes like Sangria, and which I've heard is going to be merged into the Halo 2 PSE version relatively soon, and others as well. So this space is very fast evolving. Lots of things to look into, lots of things to try. But up until I guess very recently, there hasn't been lookup arguments in other frameworks. One thing I actually saw recently is that NARC implemented the log derivative argument as well, but unfortunately, there are some practical issues with their framework that I've been trying to iron out that makes it difficult to use for ML.
Yeah, I think in the future, like Halo 2 CE version, there will also be fry at polynomial commitment scheme. So maybe you can reuse their circuit as well as you don't rely on large like field, and then you can switch easily. So yeah, that's also. And in your circuit layout, do you anticipate like there are many kind of repeated part, like for example, in the given there are many catch checks, so that people are thinking of using maybe Nova or some other more efficient proving system to kind of handle this repeated part? And do you see that also a similar pattern in ZK machine learning, so that you would maybe decompose into different components and then like, repeatedly prove for some parts and then connect different pieces together? I don't know.
Yeah, that would be ideal. There's the unfortunate thing about ML is that actually there's most architectures actually aren't exact repetitions. So it's difficult to do it's difficult to use Nova directly, but Supernova would be great. But lookups are unfortunately very critical for a large range of ML applications. So still need some developments there. But I am excited by these advances in folding schemes. So Sangria, as I mentioned, Supernova is potentially very interesting, and I saw recently that they implemented a lookup argument for, I think they're calling it Hypernova. I forgot the latest version of this. And so hopefully once that becomes public, then I'll look into that as well.
I think even you switch to Supernova, it might still maybe don't work for a case, because Supernova, like you just have multiple slots for folding different circuits. But if your circuit is not kind of repeatedly, and then it's still very hard to use, even supernova. But
Oh, I see.
there are some, yeah, I think there are some, yeah, I think supernova is like, it's still, for example, still a virtual machine. You have many different instructions and you can fold into different circuits, but if you can't fold, then like it's hard. I think there are some new advanced optimizations, which maybe you can fold different circuits by like making your kind of coefficient also become part of the witness and then like fold. But yeah, it's, yeah.
I see. Yeah, I mean, there still needs to be a lot of research to be done in this space. It's very fast evolving, and you know, what I have here is not the end all be all. So you know, in 6 months, this talk might change very completely due to the advances in proving systems and other advances as well.
Cool. Any more questions for Daniel? All right, I
great.
guess we can call that. Yeah, thanks so much for presenting to us. You know, that was really, especially the discussion at the end. That was really informative.
Yeah, and thank you everyone for coming to my talk.
All right, thanks Daniel. Thanks everybody. Bye.
Thanks. Bye.